All right, Friday before the long weekend. All right, lots of important stuff to cover today, and we'll wrap up chapter 2. So next week, we'll begin with PN junctions, PN junction diodes. Okay, let's switch to our class notebook. So we stopped here where I did a brief overview of how we create P and N-type semiconductors. So today we'll go a little bit more in depth and look at a couple of equations. Okay. So first up is a N-type material. So we had spoken about introducing dopant impurities into our semiconductor material to increase the number of charge carriers. If we take an element from column 5 of the periodic table, let's say phosphorus. Phosphorus has 5 electrons. It's from column 5 of the periodic table. So it has 5 electrons in its outermost orbit. A phosphorus atom, when implanted or introduced into the silicon lattice, will displace the silicon atom. So it's being represented right here in the center. And 4 of its valence electrons will form a covalent bond, or will form a bond with 4 neighboring silicon atoms. So let's see. Let's just say these are the electrons belonging to that phosphorus atom. So it forms a bond with 4 neighboring silicon atoms, and 1 electron is left over, which is right here. And this electron is free to move around the silicon lattice. It can move anywhere, represented by this arrow right here. So this is the free electron, the free 5th electron is free to move around. Okay, then Q minus or minus Q obviously represents the charge that is carried by that electron. So unlike an intrinsically generated electron, this free electron is not balanced by a hole. Okay, intrinsically generated electron, when it moves out of its spot, generates a hole, right? So when it generates a hole, we have an electron-hole pair. Here we have a free electron, but there is no hole to balance it out, physically speaking. The charge, however, electrically speaking, the charge of that electron is balanced out by the positive charge inside that atom, or the nucleus of the atom. So electrically, it's charge neutral. Okay. So this is charge neutral. So far, so good? Yes. So the question being asked is, what is that 5th electron doing? Right now, it's not doing anything. It's just there. It's available. It's available. It's at equilibrium. If we apply an electric field, then that electron is free to move in response to that electric field. So right now, it's just there. It's not doing anything. Okay, so this then becomes an ionized atom. And because it is donating an electron in the material, right? The 5th electron is free, so it's donating a material, donating an electron. It is also known as the donor atom. Okay, so this is also referred to as a donor atom because it is donating an electron. So again, keywords to keep in mind is donor atom. It's an ionized atom. has lost its electron or it's donated an electron. The charge, however, the overall charge in the material, of course, it's neutral because every free electron is also balanced electrically by the positive charge in that atom. Now, these positive ionized atoms are localized in the structure, but the negative electrons are free to move around. Okay, that's the key thing. So they are free to move around. Now, the number of intrinsically generated electrons and holes are balanced. And the charges that are generated here by the electrons and the positively charged donor atoms are also balanced. Okay. And then when we talk about column 3, we will introduce some equations and you will see how the overall number of charges, whether it's P or an N-type material, is all equal. Okay. All right. Any other questions? So again, no holes are created. And the charges are balanced. Okay. And of course, because you have negatively charged electrons moving around, this is known as an N-type semiconductor. Also referred to sometimes as extrinsic semiconductor because we are adding in external charge carriers. So let's move this around. Now, the opposite happens when we introduce an element from column 3, such as boron. So boron is from column 3. It has 3 electrons in its valence shell or outermost orbit. 3 of those are going to create bonds with 3 neighboring silicon atoms. Actually, it creates a bond with 4, but it only has 3 to share. It's actually borrowing 1 from the 4th silicon atom. Okay, that's show you where, let's see. Bonds with 4 silicon atoms, but it only shares 3 of its own. Okay, so in the 4th spot, there is an opening. There's a vacancy. Now, when we are flooding an intrinsic semiconductor with a whole bunch of boron atoms in a very small space, there'll be millions of these vacancies, millions and billions of these vacancies. So now, because there's an empty spot in the crystal structure, the electrons from anywhere in the lattice structure are free to jump into those vacancies. And what happens when electrons from somewhere else jump into these spots? Holes are created. And so a whole bunch of holes are created where the electrons are coming over, and those holes are represented by positive charge. And so because we're introducing a column 3 element in our semiconductor, a whole bunch of positive charges are generated. Okay. The empty spot that is created, let's say this one right here, empty spot itself does not have any charge. But because this empty spot will attract other electrons to come into its spot, it creates a positive charge somewhere else. And because the electrons will keep moving around and jumping around, we can say that the hole that is created is moving in the opposite direction. So column 3 elements will generate or create holes in other parts of the lattice. And each of those holes, of course, is also balanced by the electrons that are jumping in. So again, charge neutral. Okay, charge neutral. This vacancy here does not have any charge, does not have any charge. But if an electron jumps into this spot, right, we've seen the vacancy here. So if an electron jumps into this spot, now that boron atom has 8 electrons in it in its outermost shell. So it's accepting an electron from somewhere else. Hence, this boron atom is also known as an acceptor atom. And it is ionized because it now has one extra negative charge compared to its nucleus. Nucleus only has 3 positive charges, 3 extra positive charges, balanced by its 3 electrons, but one net negative charge, because an electron has moved into that spot. Let's take a pause while you think over all of that. And let me know if you have any questions. Yes. Yes. So the question being asked is, if you apply an electric field to this to this semiconductor, the holes would move, and the answer is yes. Physically speaking, though, it's the electrons that will be moving away from the direction of the electric field. The hole is obviously opposite. It just helps us to think of the hole as its own particle. The answer is that you're right. Yes. So the question or the statement for verification is that the entire lattice structure is neutral. The answer is yes. The entire structure is charge neutral. But the boron atom now has accepted an electron from the silicon crystal, and so it's ionized negatively, right? Negative. And because, yes, go ahead. Yes, so the donor atom, the answer is yes. Donor atom is ionized negative. Oh, sorry. Donor atom is positive, and the acceptor atom would be negative. Yeah, so donor atom has 5 electrons versus 5 protons in the nucleus, balanced by the 5 protons. It loses an electron, and so it's one less negative charge, but it has localized one extra proton, one extra positive charge. So a donor atom would be positive. That's indicated by this plus Q right here. Okay. So positive. And then the acceptor atom, it's not shown here, but would have one extra negative charge because it accepted an electron. It's accepting an electron. So again, donor donating an electron, so it has one extra positive charge. Acceptor atom is accepting an electron, so it has one extra negative charge. So ionized negatively. And then, of course, because of the generated holes, refer to this as the p-type semiconductor. P-type semiconductor. So column 3 elements, p-type material, column 5 elements, n-type material. So far, so good. Okay. All right. So charge carrier concentrations. If we have charge carriers, we have charge carriers of negative charges and positive charges. If the negative charge carriers, meaning electrons, are far larger in number than the positive charge carriers, we have an n-type material. So more electrons and more holes will result in p-type material. Okay. The number of holes and electrons would be unequal. Okay. The number of holes and electrons are unequal. Hence, we can state it's an n-type or a p-type material. The key thing is that the electrical charge is exactly the same. It's neutral, it's balanced. Okay. The key difference is that in an n-type material, the electrons are free to move. Positive charges balanced by the positive charges that are localized. And in a p-type material, the positively charged holes are free to move, and the negatively charged electrons are localized. Okay. So again, in an n-type material, the electrons are free to move. In a p-type material, the holes are free to move, but the charges are balanced. And that can be proven with this equation called the charge neutrality equation. Okay. And we'll get to that in just a minute. Few more definitions before that. There are majority carriers and minority carriers. Simply refers to the number of charge carriers. So in an n-type material, electrons and holes are present due to both thermal generation, intrinsic generation, as well as extrinsic doping, right? So in an n-type material, the number of electrons are larger, but there are electrons that are available due to the addition of impurities, and there are electrons and holes available due to thermal generation. So the number of electrons is far larger than the number of holes. Hence, in an n-type material, let's do this breakdown. Majority carriers and minority carriers. In an n-type material, the number of electrons are the majority carriers. And holes are the minority carriers. And in a p-type material, the exact opposite. Holes are the majority carriers and electrons are the minority carriers. Let's do H plus. So this simply refers to the pure number of charge carriers. Okay, so majority and minority carriers. Yes. Okay. Then the pure number is defined by its concentration per cubic volume in the material. And so ND and NA are basically the number of atoms per cubic centimeter. And because ND and NA are defined per centimeter or per cubic centimeter. Many of the equations are also based on using the centimeter as the unit. But again, the important thing to keep in mind is when you're performing your calculations, you need to ensure you're converting everything. The centimeter would be 10 raised to minus 2 meters. Okay. If it's a micron, if something's given in micron, then it's 10 raised to minus 6. Otherwise, your answers would turn out to be incorrect. Especially when you are using the online system and you're entering your answers, many of the units will be in centimeters. So for me, some people are very quick to do it. For me, it takes a little while. So what I do is I'll convert everything into my equation, 10 raised to minus 2, 10 raised to minus 3, 10 raised to minus 4, 10 raised to minus 6. I'll perform all my answers and perform all my calculations based on that, converting everything to standard meters. And then, depending on what is being asked, like if the units are simply meters, then I'll just enter the answer. In the system, the online system, it asks you for answers in centimeters, and I'd convert it back to centimeters. Okay. So please be careful when you're doing that. Okay. So as I was saying, this is basically defined as atoms per centimeter cube. And this is controlled in the manufacturing process. We say we are introducing an external impurity and the dosage is such and such. The dosage is 10 raised to 16 atoms per centimeter cube, or the dose is 10 raised to 20 atoms per centimeter cube. So that's the dosage. Yeah, the dosage basically literally simply means the number of atoms you're introducing into our semiconductor material. And so again, dosage is also in atoms per centimeter cube. Typical dosage is about 10 raised to 14, 10 raised to 21 centimeter cube. Sometimes if you're reading a different book or written by a different author, it'll just say per centimeter cube. Atoms are just assumed. Okay, it'll just say per centimeter cube. All right, overall charge. Any questions so far? Yes. Yes, that's 10 raised to 14. 14 to 21. Okay, charge neutrality. Q, of course, is the one individual charge. One individual charge. Nd and Na are the number of donor atoms, number of acceptor atoms. P and N are the total number of holes and the total number of electrons that are present in a material. Okay. Yes. So this one or this one? Atoms per centimeter cube, yes. But let's say we're just talking about one single material with 1 cubic centimeter. Right? So Nd and Na doesn't matter if you're looking at 1 cubic centimeter of material or half cubic centimeter of material. We'll just say it's like 1 unit of material. And inside that unit of material, if you have some concentration of donor atoms, some concentration of acceptor atoms, and then the total number of holes and the total number of electrons in the atom, if we sum up all the charges, it'll turn out to be 0. And here's the reason why. Let's say, for example, charge neutrality equation. Let's say we dope a semiconductor material with simply donor atoms. Okay, just donor atoms. No acceptor atoms. So then what are the charge carriers that are present in that material? We'd have, sorry, negative charges, right? So what would we have? let's first define, let's say total number of P would be P intrinsic plus P extrinsic. And then total number of N charges be N intrinsic plus N extrinsic. Right? That will be total number of holes, total number of electrons. Number of holes, total number of electrons. The intrinsic are, of course, thermally generated. So they're always balanced. If an electron moves out of its spot because of thermal effects, then a hole is created. So the intrinsic carriers are always balanced. Okay, it's only the externally introduced electrons or holes that are not balanced. So if we have a semiconductor material, we insert only donor atoms in there. Donor atoms means column 5, extra electron, it's donating an electron, right? So each atom that donates an electron is going to have positively charged donor atoms. Now, because it has lost its electron, is a positively charged or ionized donor atom. And it's balancing out the electron, the negative charge of the electrons that is free to move around. So an ionized atom would be equal to an electron that is freely moving around in there. And this electron is NEXT. So the number of ionized donor atoms would be equal to the total number of extrinsically generated electrons. So charge neutral. Let's take a pause, think over that, if you have any questions. Yes.
Balanced by the protons in the donator atoms?
Yes. So question being asked was, each electron is each electron balanced by the protons in the nucleus of the donor atom? The answer is yes. All right, let me see if I understand this. So your question is, wouldn't ND plus, the ionized atoms, be balanced by, what is the second? Yes, yes. So, okay, I got you. So ionized donor atom is equal to E minus. That E minus simply represents the electron that atom has lost. That's it, all it's representing. It's not representing anything else. It's simply ND plus each donor atom, each ionized donor atom is equal in charge to the electron it has lost. So let's donated electron. And hence, if there are 10 donor atoms, there'll be 10 free electrons. But everything is balanced out, right? The electrons are free to move around, but the positively charged atoms are localized in this silicon lattice structure. And then the intrinsic holes and the intrinsic holes and intrinsic electrons are already balanced. And so overall, it is charge neutral. If we introduce column 3 elements in there, now Na acceptor atoms are going to create holes, positively charged holes in there. But because positively charged holes are created and electrons are jumping into the empty spots, again, it is charge neutral. Okay, so overall, the charges are always neutral. That makes sense to everyone? Okay. Now, when we introduce a large number of charge carriers in there, oh, actually, I jumped one step ahead. So to calculate the number of electrons and holes that are generated, we have these equations. If the number of donor atoms is far larger than the number of acceptor atoms, we can determine the number of charge carriers. Now, the N here is simply the charge carriers that are generated, okay? So the number of charge carriers that are generated is given by a quadratic equation, okay? Nd minus Na square root of Nd minus Na square plus 4Ni square. Here we have an excess of negatively charged electrons in a p-type material. We have excess of positively charged holes. Exactly, not exactly the same, but similar equations, but Nd and Na are flipped. Yes. Yes. And the other N is referring to hole concentration. So this would be the number of charge carriers. Sorry, go ahead. Yes. Yeah. It'll be specified. So I won't be vague. So hopefully there won't be any confusion, and I'll be there if there's any confusion. So in an N-type material, Na would be 0. In a p-type material, Nd would be 0. We would not want to dope with both acceptor and donor atoms. Okay. If you're trying to create an N-type material, meaning we want an excess of electrons, then we do not want Nd to be in there. Okay. Now, one result of having these excess charge carriers in there is that the mobility decreases. The mobility decreases. So in simple terms, let's say if we flood in a small amount of space, we flood in a whole bunch of carriers. Well, now, simple terms, it's crowded. And when it's crowded, the ease with which it moves through the structure is reduced. Hence, mobility, which measures the ease of movement, decreases. So with increasing concentrations, the mobility ends up saturating. Right around here. So 10 raised to 18, 10 raised to 19, 10 raised to 20 atoms per centimeter cube. That is far larger in number than the intrinsically generated electron hole pairs. Okay, so the mobility of these charge carriers decreases. But at the same time, it has a far larger effect on resistivity because of the sheer number of charge carriers now, we can have far larger currents moving through that semiconductor material. Okay. And so while the mobility decreases, it has the opposite effect on the electrical characteristics. And also yes. Sure. So let's go here, this one. Okay. Okay. So the mobility equations are given here. Standard equation. Let's see. Okay. So the currents that occur in a semiconductor material are of two kinds. One is a drift current, the other one is a diffusion current. Okay. So drift current, as the name suggests, is the movement of the charge carriers in response to an applied electric field. So we have free electrons or we have free holes that are available for conduction. If we apply an electric field across a piece of semiconductor material, the electrons will drift away from the direction of the field, and the holes will drift in direction of the electric field. Okay. I'm hoping students are familiar from the prereq physics classes a little bit. But when you apply an electric field to an either N-type or P-type material, electrons will drift away from the direction of the field, and holes will drift in direction of the electric field. And so that current is known as the drift current. So total current occurs due to two different phenomena: drift and diffusion. And drift is basically the movement of charge carriers in response to an electric field. Okay. And then there's diffusion. The diffusion occurs because of non-uniform doping concentrations. So when we have an N-type or a P-type semiconductor material, the concentration is not going to be uniform, not for the material, right? And so in diffusion, electrons and holes diffuse to create uniformity. Like any other physical quantity, if you hold up liquid at a high level, if you give it a space, if there's enough space for it to move around, liquid's going to diffuse until it forms a flat line, right? Temperature goes from high to low, pressure flows from high to low, electrical current or charge also goes from high to low. So if there is a higher concentration of charge carriers in a material, it's going to diffuse through the material until the distribution of those charge carriers is uniform throughout the entire material, subject to laws of physics. Okay. And the current that occurs due to this diffusion is known as diffusion current. So as we go along this path right here, the concentration gradient is higher at this end. Not concentration gradient, the concentration is higher. And here, concentration is lower. And so the charge carriers diffuse in response to the non-uniform doping, trying to level out. And that current is known as the diffusion current. And total current is the sum of drift as well as the diffusion current. This phenomenon is going to be important when we look at p-n junctions, okay, p-n junction diode, because we'll bring p and n type materials in close contact, and when that happens, there is a non-uniformity right at the junction. So the carriers diffuse through the junction. Okay. All right. It's about 9 minutes left. There's another quantity that we will use in many of our equations, known as the thermal voltage. Thermal voltage occurs due to two dissimilar semiconductor types. Okay. Vt is the thermal voltage. K is the Boltzmann's constant. T is temperature in Kelvin. And Q is 1 unit charge. Now, typically, when we perform this calculation, it turns out to be about 25.8 millivolts. And it's funny about this is, depending on the book, sometimes it's 25.8. I've seen 25.9, depending on how many decimal places you take in your answer. But it's approximately 25.8 at 300 Kelvin. If you're taking Boltzmann's constant in electron volts per Kelvin, then you would not do K over Q. Simply multiply by temperature. Okay. Yes. So thermal voltage is a parameter that we will use in many of our equations, specifically the standard diode equation. Let's simply describe is the voltage that is naturally occurring due to the thermal movement of charge carriers. Similar to the voltage that could be generated between two dissimilar metals at two different temperatures. Yes. Yes. Sometimes, more often than not, I feel it's simply a constant to use in an equation. And several authors do, several researchers and scientists do use it the same way. Just use it as a constant at any temp. At a particular temperature. Reverse the potential by heating at, and you heat at the other end. Maybe to generate voltage. Honestly, I don't know. That's an interesting question. Could we increase or reduce the thermal voltage if we heat the material at the other end? Honestly, I don't know. I'm sure it's possible. Okay, so just a couple more slides in the last 5 minutes. We talked a lot about semiconductor physics, right? From this point on, we'll deal with a little bit of semiconductor physics for each of our devices, and then the primary objective is to look at circuits, right? Circuits with these devices. So there's, of course, when we take these devices, insert them into a circuit or build a circuit using these devices, there is movement of electrons and holes, but we are not going to delve too deep for every single device. And that's a higher level class. That's solid state electronics, EE 534. Okay, so if you're interested, we can take that class when it's offered. But going forward, chapters 3, 4, 5, 6, and 7, we'll look at circuits dealing with these devices. So how do we actually manufacture these devices? Okay, and that's what I want to talk about in these last 2 slides. So going back to the beginning of chapter 1 and 2, I did a little small talk about how the integrated circuit was created, how it was invented around the 1950s. What they did was, well, actually, let's not talk about that integrated circuit. We have a semiconductor material, right? And the reason we say it's an integrated circuit is because we are taking large number of components and we are integrating into it one small piece of semiconductor material. I always like to describe it as a printed circuit board, PCB, at the microscopic scale. That's all it is, right? A PCB is nothing but a board that carries wires for connections between multiple components. So an integrated circuit is exactly the same, except the difference is we create the devices inside the semiconductor material itself, and then we can use the semiconductor material, add some more material on top to create wires making connections between those components. Hence the name integrated circuit. So the way we create this is something known as microelectronic fabrication. Okay. And microelectronic fabrication requires a highly specialized skill set. Okay. There is a class that is offered every single winter here at Cal Poly. It's only offered once a year. It's under BMed 434. Associated lab is BMed 435. It's cross-listed with EE. It's EE 423 and EE 473. And it's a class that takes place in Engineering 3 in a facility called the clean room. How many of you are aware of the class and of the facility? Just 3, 4 people. That's good. So the reason the facility is called a clean room because it literally is clean. So for instance, if you're trying to create a printed circuit board, you're running a wire from point A to point B. Now, while you're creating that board, if there's a break in that wire, right? The wire is just flat. There's a break in the wire. Maybe there was a contamination of some particles or something, and there's a wire does not cross from point A to point B. There's a break in the middle. Devices are not going to work, right? So now when you create integrated circuits, the same principle applies. You're trying to create a wire from point A to point B, except it's now microns or less, the feature size. So if the wire is less than a few microns, even dust particles at that size are look like huge boulders. So if there's a tiny dust particle in the middle of your pathway, the wire is not going to work. So we require a specialized facility where the air is continuously filtered of these particles. So hence the name clean room. Okay. So to give you an idea of how clean it is inside that environment, in a standard cubic centimeter volume of air right here in this classroom, we could have about 1 million or 2 million particles of size 0.5 microns or less. In a clean room, it is typically around 1,000 or less. High spec clean rooms are class 100. Even higher ones are class 10, class 1, or even less. Production facilities have stringent requirements. They are working at the nanoscale, and so their class sizes are even lower than that. The clean room year that we have at Cal Poly is class 1000. The clean room where I did my doctorate research was class 1000 with a couple of specialized bays with class 100. When I was at UCSB, they also had class 100 and class 1000. Again, all has to do with keeping the environment clean. We work with a lot of hazardous chemicals in there. So there's a safety training that is required of every student who comes in there. But it's a class you can take next year. So if you are, I'm assuming you'd be in your junior year right around this time. So when you get to your senior year, that is an option to study semiconductor fabrication if you want. We are out of time, so if you have to leave, you can leave. I'm just gonna cover a couple more things here. The way we fabricate it is, this is looking at the cross section from the side, is we deposit some material and we etch it. So if we want to create a wire, then we would deposit a whole bunch of like metal on top, and we would etch or pattern that metal. Okay, so it's all deposit and etch cycles, and we create openings in the silicon. When we create openings in the silicon, we can implant or diffuse . implant or diffuse external dopants. Okay, and so each one of these processes is specific. If you want to create an implant inside a semiconductor material, process is known as ion implantation. If you want to diffuse it, it's known as diffusion. Okay, and so you create an opening in your semiconductor and you implant or diffuse external atoms in that semiconductor material. Thus, you can create a small section of either a p-type or n-type material inside your semiconductor device. And then we can come back, create more openings, and create metal contacts. Metal contacts. So that metal contacts is basically just wires running from point A to point B on top of our semiconductor material. Okay. So again, this is just a small 2-slide overview of what semiconductor fabrication looks like. Again, we have several classes that can cover this process. All right, so we'll end class here today. Friday quiz. If you have not yet read the announcement, I was posted yesterday, and so you have from 8 a.m. today until midnight today to get that done. All right, I'll bid you a good weekend, and I will see you all on Tuesday. Tuesday. Remember, Monday is an academic holiday. I'll see you all on Tuesday, and we'll have Monday quiz number 2. Okay, that will be based on the material we covered Monday, Wednesday, Friday of this week. All right. Yes. Okay.